Hey y'all, today I'm going to be talking about resonance in RLC circuits. So I've drawn an RLC circuit on the board. Consists of a resistor, an inductor, and a capacitor with the equivalent terms. A resistor, an inductor, and a capacitor all impede current. So before we talk about resonance, we need to talk about impedance and what that looks like mathematically. So impedance, obviously, like I said, it goes against the current. So let's talk about peak voltage. So right now we have an alternating current, which is going to have some sort of frequency. And so let's talk about the voltage and what that looks like in terms of impedance. So we have this equation, which is equal to the peak voltage of the whole thing. But since they all impede each other and they're at different frequencies, they all have a different voltage. And the equation looks like this. With our V0 squared, or of the resistor, and then we have so it is the voltage of the inductor minus the voltage of the capacitor, squared, all under the square root. Now we need it in terms of impedance, and impedance is used with the term Z. So we have these equations for Ohm's law, and these are the XC and XL are the reactants that are discussed in the previous section, which we won't go into today. But if we go ahead and substitute these equations in for the values we have here, we get this equation. I0 times by impedance is equal to the square root of I0 times R squared plus the quantity I0 times by XL subtract I0 times by XC, that quantity squared. Now with basic algebra, we're able to pull the I0 out from underneath this square root, and we will get I0 times Z, which is our impedance value, is equal to the square root, I0 times the square root of R squared plus XL subtract XC squared. Now our basic algebra as well shows that we can cancel out these I0s, which gives us the equation for impedance. So Z is equal to the square root of R squared plus XL minus XC, that value squared. So now that we have the equation for impedance, which is shown right here, we can talk more about what resonance is. So I have these sinusoidal waves drawn on the board here. This is the equation, or the wave, that is what a current would look like. And that is equal to the voltage of overall. So now we see that the resistor current is equal to the voltage current, and that the voltage for the inductor and the voltage for the capacitor are out of phase with each other, which makes it cancel each other out, which makes it as if the voltage is just being affected by the resistor because of this canceling out of phase with each other. And that will look like, mathematically, XC is equal to XL. And if we put that into our equation, we'll find that Z would then therefore be equal to R. We know that since XC equals XL, that the resistance is equal to, the impedance is equal to the value of the resistor. Now let's talk about the resonant frequency that occurs to make this happen. To do that mathematically, we have some equations of what XC and XL equal. Those are also equations that were derived in a previous section, which we will not go into today. But mathematically, since we know XC equals XL when it is in a resonant circuit, we know that this will equal this equation. Now some math that we can do, some algebra we can do to get F0 by itself makes it so that F0 equals 1 over 2 pi the square root of C times L. And that is our resonant frequency. And that is what we can solve for when we are looking at resonance within an RLC circuit. Resonance frequency is very useful in radios and how that portrays. To have a resonance frequency, or to solve for it, is very useful to know when making a radio. We can use these equations to calculate the resonance frequency, and that really does help us to know what size capacitor to use in a circuit and how the resistor works within an alternating current circuit. Now photosynthesize with George!